Hello everyone, welcome back. In this particular video, we're going to talk about the Malonic ester synthesis. Now, this reaction is a very specific reaction that's useful for synthesizing alkylated acetic acids. This reaction uses the malonic ester, and you can synthesize carboxylic acids. Now, specifically, as I will show later, this carboxylic acid can be treated as a derivative of acetic acid. So it can synthesize carboxylic acids from malonic ester by alkylating at the alpha carbon. The product is an alkyl acetic acid. Now, in some cases, it may be a di-alkyl acetic acid. Now, the alkyl group in the acetic acid, this is coming from the alkylation that we are doing on the malonic ester. So let's look at a generalized example first, and then we will go into some specific examples. So let's look at this example here. So this molecule here, this is the malonic ester. This is diethyl malonate. Okay, this is the malonic ester that we're using. So malonic acid is a 3-carbon carboxylic acid. 1, 2, 3. So it's a 3-carbon dicarboxylic acid. And what we're looking at here is the ethyl ester of that dicarboxylic acid. Now, as far as the malonic ester is concerned, notice that there is an alpha carbon here, and this carbon is alpha to both ester groups, and there are 2 alpha hydrogens on that alpha carbon. And because this alpha carbon is between 2 ester groups, that means that these alpha hydrogens are pretty acidic compared to other alpha hydrogens because they are between 2 acyl groups there, or 2 ester groups. So this is the generalized reaction that I've shown here. So you first treat your diethyl malonate or the malonic ester with a base. And since this is an ester, notice that the base that I'm using matches the alcohol part of your ester. Okay, so sodium methoxide is the base that I'm using because this is an ethyl ester of the malonic acid. And then you treat it with an alkyl halide. And when you follow that up with a hydrolysis, an acidic hydrolysis, and if you heat this reaction, then your product is an alkyl acetic acid. So notice that this molecule here, we can treat this as a derivative of acetic acid. What's boxed here is a 2-carbon carboxylic acid. So that's acetic acid. And what this is basically an acetic acid that is substituted with an alkyl group. So that's why we're calling it an alkyl acetic acid. Let's look at the mechanism, but before that, let's also try to match the product with the reactant here. So if we compare the reactant to the product, it seems like we're keeping one of these ester groups, or one of the acyl carbons is retained in the product. The alpha carbon here, that's this carbon. So the carbon that is the acetic acid carbon, the CH2, the methylene here, that is the alpha carbon from the malonic ester. And we are keeping one of the ester groups, which becomes a carboxylic acid, and we lose the other ester group in the process. So let's look at the mechanism here. Again, this is not a very detailed step-by-step mechanism because this reaction here incorporates mechanisms from other sections that we've already covered. So we're just going to skip over some of those and then go talk about the details of this mechanism itself. So since we have the first step as the malonic ester reacting with the base, the initial step is going to be a deprotonation. Okay, so we're going to create the enolate here. So we start with the diethyl malonate. I can draw out one of the alpha hydrogens. When we react this with sodium ethoxide, which is the base here. The ethoxide is going to deprotonate the alpha hydrogen, and that would leave the electron pair on that alpha carbon. And this reaction would be favored in the forward direction because this alpha hydrogen is pretty acidic. The pKa for this hydrogen is like around 12 to 14 approximately. Around 12 would be a good number to put there. So approximately around 12 is the pKa for that acid. So this would give us the enolate. Now, notice that what I've drawn here is the resonance form of the enolate. This structure, the conjugate base here, this is resonance stabilized and it can give us the enolate. We're just going to draw this form. And plus, the ethoxide is going to become ethanol. So that's the first step. So we get the enolate in this particular step. Second, we react this with alkyl halide. So when we reacted with the alkyl halide, the enolate being a nucleophile would go attack the R group. This reaction here, this is an SN2 type of attack. So that means it works best with methyl or primary alkyl halides. So all of the limitations of SN2 reactions, they are applicable here. So we do that. And this would give us the substituted malonic ester now. So give us a substituted malonic ester. So we get the ester. Now, at this point, in principle, there's another alpha hydrogen left on that carbon, which means we can deprotonate again using another equivalent of sodium ethoxide and add another R group. That R group may be the same or it could be different, but there is possibility for another alkylation here. For the purposes of this mechanism here, we will just skip through that and we will not discuss that yet, but we will go look at the next step. What is going on here? How does this ester become the alkylacetic acid? Okay, so the next step here is the reaction with the acid. You're heating it with acid. So we have acid and we are heating this. So we have an ester and we reheat it with H3O plus. That is the ester hydrolysis reaction. Okay, so the ester can get hydrolyzed. So since this is a diester, it will get hydrolyzed to the dicarboxylic acid. So what we're going to get initially is the dicarboxylic acid here. That's the ester hydrolysis. So the reverse of a Fischer esterification. The ester gets hydrolyzed. Now, so that's the dicarboxylic acid. How do we end with the alkylacetic acid? Now, that's the most important thing in this reaction, or that's the key step in this reaction, something that we haven't seen before. Now, I can rewrite this alkylacetic acid is slightly differently. Okay, this molecule here, I can rewrite this as, and all I'm changing is just the orientation of how things are written here. Okay, I'm drawing that carboxylic acid slightly differently. This carboxylic acid here, this can be called a beta-keto acid. Beta-keto acid. And what that means is we have a carboxylic acid. Remember, this carbon was the alpha carbon, and on the beta carbon there is a C double bond O. It is an acyl group here, but it's a C double bond O. It could also be a keto group, like just a carbonyl group. In this particular case, it is an acyl group, but that's fine. So whenever you have a C double bond O, that's beta to a carboxylic acid, we can call it a beta-keto acid. And the beta-keto acid has been rearranged, or not rearranged, it has been rewritten in a different orientation. So what beta-keto acids do is, when you are under acidic conditions and when you're heating it, the beta-keto acids can undergo some rearrangement here. And essentially what happens is, the pi bond here, it can go and deprotonate that hydrogen, okay, which is equivalent to using a lone pair here for doing the proton transfer and using the pi bond later. You could do it in 2 steps, but you can show it like that. So, and then simultaneously, the single bond here becomes a double bond between the carbon and the oxygen, and it breaks the single bond here between the alpha carbon and that other acyl carbon. So if we look at the fragments and if we try to redraw what we got here, what we have is we have a OH, which is connected to a carbon-oxygen single bond now. And this oxygen should have a hydrogen on it. There's a double bond here, and there is an R group here, and this is our alpha carbon. Along with it, okay, plus, if you look at it, there's a carbon which is double bonded to one oxygen, and there's a double bond to another oxygen. That's what we're seeing. So we have a carbon that's double bonded to 2 oxygens. This is carbon dioxide. Okay, so we lose one of the carboxylic acid groups as carbon dioxide. This step is called a decarboxylation. Okay, this is a decarboxylation. We are losing carbon dioxide. And what we get as a result of it, if you look at this, this is the enol of a carboxylic acid. We've got the enol of a carboxylic acid, which can tautomerize. And remember, with tautomerization, what happens is the hydrogen here ends up on the alpha carbon. The double bond comes between the carbon and the oxygen. So what we're going to get is a carbon-oxygen double bond, 2 lone pairs here. And we will have the R group here. Now, we haven't drawn a complete mechanism for the tautomerization here, but this process is facilitated by acid. So the acid is what helps with this process, but under acidic conditions, that enol can tautomerize to the keto form, which is a carboxylic acid. So that is how the malonic ester is converted into an alkyl acetic acid. Now, what we have is an alkyl group connected to the alpha carbon, and we've got an alkyl acetic acid. Next, we are going to look at some examples of the malonic ester synthesis, see how it can be applied for the synthesis of alkyl acetic acids. So what we have here is the first example where the diethyl malonate is first treated with the base, followed by a reaction with propyl bromide and aqueous workup with heating. So you're heating it with acid. So let's work through the steps here. So in the first step, when you react it with the sodium ethoxide, that's going to deprotonate the alpha hydrogen here. So the alpha hydrogen would be deprotonated. The electrons would land on that alpha carbon. That would give us the enolate. Now, I want to remind again that what we're drawing here is a resonance form of the enolate. We're not drawing it in the enolate form, but this is a resonance form of the enolate, which means it is the enolate, okay? The next step, this reacts with the propyl bromide. Okay, so as far as the propyl bromide is concerned, this carbon here is the alpha carbon, that's the partial positive carbon. So the nucleophile goes and attacks this carbon. The bromine is going to get kicked out. Propyl bromide is a primary alkyl halide. That means this SN2 reaction is going to work really well. Okay, so we get the alkylated diethyl malonate now. So there were 3 carbons here. And if you notice, to the alpha carbon, which was the nucleophilic center, I've added 1, 2, and 3 carbons. So I've added that propyl chain to that alpha carbon. Now, when we do the hydrolysis, H3O plus, when we do the hydrolysis, the diethyl malonate will hydrolyze to the carboxylic acid. The propyl chain is still here. That's the alpha carbon. 1, 2, and 3 carbons. So that's the malonic acid. And as we saw earlier, under the reaction conditions, when we are heating this beta-keto acid under acidic conditions, it's going to get converted into the alkyl acetic acid. Now, in going from this alkyl malonic acid to the alkyl acetic acid, it's pretty simple. Essentially, what we're doing is we're getting rid of this, okay, the carbon dioxide. Okay, there's carbon, there are 2 oxygens. The hydrogen here eventually ends up on the alpha carbon through the tautomerization process. So if you basically remove that carboxylic acid group and or remove that carboxylic acid group as carbon dioxide and add the hydrogen to this alpha carbon, whatever is remaining is the product. So in this particular case, our product is going to be the alpha carbon plus 3 additional carbons. So 1, 2, 3. Here's 1, 2, and 3. So essentially what we made is, here's our acetic acid. So we've created an alkyl acetic acid with a 3 carbon chain. Now, we won't call this the alkyl acetic acid. This overall has 1, 2, 3, 4, 5 carbons. So what we've made here is pentanoic acid. So we've made a 5 carbon carboxylic acid. So we converted the diethyl malonate into the pentanoic acid here. Let's look at the second example where we are trying to do 2 alkylations, because recollect, the diethyl malonate has 2 alpha hydrogens, so we can do 2 substitutions here. So let's start here. Start with the first step. The alpha hydrogen is deprotonated by the sodium ethoxide. Deprotonates, gives us the enolate. Negative charge over there. We react this with methyl bromide. So prime methyl halide, very good for SN2 reaction. So the goes and attacks, the Br gets kicked out. So we're going to get the alkylated malonic ester. There is a methyl substituent on that alpha carbon, and it is the alpha carbon that we are focused on throughout. Okay, so the alpha carbon. And at this point, there's another alpha hydrogen because there were 2 alpha hydrogens to start out with. So when we react this further with sodium ethoxide, The sodium ethoxide can now go and deprotonate the other alpha hydrogen. Electrons go to that carbon, the alpha carbon, and so we get a new enolate here. So we'll have the methyl group and we have the enolate over there. So we have a different enolate this time. Okay, this is a methyl group here. And now we are reacting this with this isobutyl bromide. Okay, that's the other one. So the nucleophile goes and attacks the carbon here. The bromine gets kicked out. So we are adding an isobutyl group also to that alpha carbon. So our product here is going to be OET with a methyl group that we added initially in the first step and an isobutyl group. Now this carbon here, which was the electrophilic carbon, is what's going to be connected. So we're going to have an isobutyl group connected to that carbon. This is followed by the acidic hydrolysis and the decarboxylation. So when we do the H3O plus under acidic conditions, this is going to hydrolyze to the beta-keto acid product or the dicarboxylic acid here. So we're going to have methyl and we are going to have the isobutyl group over there. And as we saw previously, under these conditions where we are heating it with acid and heat, both of these steps are happening under those conditions, the hydrolysis and then the decarboxylation. So under these conditions, essentially what we have to do is remove one of these carboxylic acid groups as carbon dioxide. The hydrogen comes to this carbon, and then we preserve everything. So if you look at it overall, that's your alpha carbon, alpha carbon, alpha carbon. And so I'm going to draw acetic acid. Here's our alpha carbon. And on the alpha carbon, we should have a methyl group and we should have the isobutyl group. So that will be our product that we get. So that's the final product from this reaction. And we've added two alkyl groups to that alpha carbon. So that's the utility of this malonic ester synthesis. Now you can also work backwards. If you're given an alkyl acetic acid, you can look at the alpha carbon to identify what substituents are connected to the alpha carbon. And that helps you work backward and predict what alkyl halides were brought in. So in this particular case, our alpha carbon of the alkyl acetic acid or this carboxylic acid here has a methyl substituent on the alpha carbon, and there is an isobutyl substituent on the alpha carbon. So essentially, to identify the alkyl halides, what we do is we add a halogen to the groups. So we had a halogen to the methyl, so it could be methyl chloride. We use methyl bromide here, but it could be methyl chloride or methyl iodide. And we add a halogen to that carbon, and that would give us the halogen that was used for making that particular alkyl acetic acid. I hope you find the discussion of the malonic ester synthesis and the solved examples helpful.